Section: Introduction. In this section, we delve into the topic of large language models, LLMs, and the practice of instruction fine-tuning. This process involves adjusting LLMs to better respond to human prompts, enhancing their performance and ability to generalize. Fine-tuning is a delicate task that requires expert knowledge to ensure the instruction dataset is both diverse and high quality. However, it also involves a significant investment in manually collecting annotations, particularly for alignment purposes. To mitigate these costs and challenges, some practitioners opt to use synthetic data generated by pre-instructed models like Bard, ChatGPT, or Claude. This approach has been employed to create instruction data for many recent LLMs. Sometimes, this happens unintentionally, such as when workers use outputs from ChatGPT to complete their tasks. This practice raises legal and ethical questions about whether the fine-tuned model is essentially a derivative of the original model. It's crucial, therefore, to figure out how to detect when LLM outputs are being reused as training data. Detecting synthetic texts has become increasingly difficult, which is particularly concerning when such texts could be used for harmful purposes. One strategy to tackle this issue is watermarking. This involves embedding a secret marker in the content during or after its creation, making it possible to trace the content back to the model that generated it. Watermarking has been around for a while, but its application to generative models, especially LLMs, has seen a surge of interest due to recent advancements that allow for efficient detection with minimal impact on output quality. Given these developments, our study seeks to answer a critical question: what happens when watermarked texts are used as fine-tuning data? We introduce the concept of radioactivity in the context of LLM watermarking. This metaphor describes the potential of watermarked text to contaminate a model when it's used for fine-tuning. This issue is somewhat related to membership inference attacks, MIA, which aim to determine if a specific piece of text was used in a model's training. However, MIAs usually require access to the model's detailed predictions, or logits, which might not always be available. In contrast, watermarked texts are expected to leave a detectable trace at the corpus level due to their repetitive nature, making it possible to identify training on watermarked texts even without knowing the specific texts involved. Our contributions to this question include developing new methods to detect this radioactivity under 4 different scenarios, based on whether we have access to the fine-tuned model, open or closed, and the training data, supervised or unsupervised. Notably, our method for open model detection significantly outperforms the baseline approach. We also demonstrate the presence of radioactivity in a real-world scenario where an LLM was fine-tuned on watermarked texts. Our tests were able to detect this radioactivity effectively, even when a small portion of the fine-tuning data was watermarked. Additionally, we explore how the process of contamination works, finding that certain conditions, like small windows for watermarking hashing, can increase radioactivity. Furthermore, we provide a background on membership inference attacks, MIAs, which aim to identify whether a specific sample was part of a model's training data. MIAs are particularly relevant in the context of generative models, where they can reveal if an entire dataset was used for training or even reconstruct some of the training data. Depending on the situation, MIAs can breach the confidentiality of sensitive training data or expose training on prohibited data. Regarding watermarking for LLMs, recent methods have focused on altering either the probability distribution or the sampling method for generating the next token in a sequence. The detectability of a watermark in generated text depends on the text's entropy. Our focus, however, is on identifying whether a model has been contaminated by training on watermarked data. This requires detecting a subtle but statistically significant watermark signal across a large volume of text. Our approach is particularly concerned with unintentional contamination, where the training on watermarked data happens without explicit collaboration or awareness between the parties involved. We also address scenarios where only a small fraction of the training data is watermarked. While watermarking is also used for protecting intellectual property, our study is more focused on the radioactivity of watermark texts and their detectability in AI-generated content. Section Summary. In this section, we explore the concept of using watermark texts as fine-tuning data for large language models, LLMs. We introduce methods to detect the radioactivity of watermark text, which can contaminate a model during fine-tuning, even when the specific watermark texts are unknown. Our study focuses on detecting this contamination in different scenarios, showing that watermark text can significantly impact the model's behavior, especially in real-world settings like fine-tuning on self-instruct output. Section: Technical Background for LLM Watermarking. In this section, we delve into the technical foundations of watermarking techniques for large language models, LLMs, specifically focusing on those that modify the LLM's decoding process due to their effectiveness and practical application. We explore a scenario where a decoder-only LLM takes a sequence of tokens as input and outputs a vector of logits. These tokens are part of the model's vocabulary. The vector of logits produced by the LLM is then converted into a probability distribution of the next token through a process known as softmax. The generation of text occurs by selecting the next token from this distribution using various methods, like top-K sampling or nucleus sampling, appending this token to the existing sequence, and repeating this process. The process of embedding a watermark involves altering either the logit vector or the sampling method based on a secret key. Typically, the output from a secret-keyed cryptographic function, which hashes the previous tokens, is used. This output acts as a seed to initialize a random number generator, which then influences the selection of the next token. For instance, this might involve creating a list of preferred tokens where the sampling probability is increased. When it comes to detecting the watermark, the process involves tokenizing the text in question, regenerating the secret seed, and then scoring each token based on a real-valued function that considers the token in relation to the seed and the sequence of tokens. A statistical test, which might look at the number of preferred tokens in the text, is then used to determine if the text contains a watermark. We provide more detailed explanations in the appendix. Moving on to the scenarios of interest, we imagine a situation where a model owner, whom we'll call Alice, has developed a proprietary language model fine-tuned for specific tasks like chatting, problem-solving, or code generation, and made available through an API. Another individual, Bob, has his own language model. Alice suspects that Bob has fine-tuned his model using some outputs from her model. We denote the dataset used for fine-tuning Bob's model, which includes texts generated by Alice's model. We also define a proportion that represents the amount of Bob's fine-tuning data that originated from Alice's model. We outline 4 main scenarios based on Alice's ability to access Bob's model and fine-tuning data. In the first scenario, Alice has direct knowledge of Bob's training data because Bob used an identifiable account to query Alice's model, allowing Alice to retain all the content generated for Bob. In the second scenario, Bob either doesn't use an identifiable account or conceals his identity, making it the most realistic scenario. The other 2 scenarios focus on Alice's access to Bob's model, either through open model access, where Alice can input data into Bob's model and observe the output logits, or through closed model access, where Alice can only see the generated texts without access to the underlying probability vectors or logits. Lastly, we introduce the concept of radioactivity in the context of statistical testing. If a statistical test can confidently assert that Bob's model was not trained on a specific dataset or outputs from Alice's model at a certain significance level, we say the dataset or Alice's model is radioactive for Bob's model. The level of radioactivity is quantified, with a low value indicating strong radioactivity, high confidence in detection, and a high value indicating weak radioactivity. Detection is akin to a random guess. Section Summary. In this section, we delve into the technical background for LLM watermarking, focusing on methods that modify the LLM decoding process for improved performance and practicality. We explore a decoder-only LLM that takes a sequence of tokens as input and generates a vector of logits, which is then transformed into a probability distribution for the next token. The watermark embedding process alters either the logit vector or the sampling procedure based on a secret key, influencing the token generation and enabling watermark detection through statistical tests. Section: Radioactivity Detection. In this section, we explore methods to identify whether text has been marked with radioactivity, which means checking if a text has been influenced by a language model's training on specific data, both for texts that have and haven't been watermarked. We tackle this in various scenarios as outlined earlier. Without watermarking, in scenarios where the model's workings are transparent and it's being closely monitored, we assess the radioactivity of a text by looking at how the model reacts to it, specifically through its loss or perplexity values. Perplexity measures how well the model predicts a sample. It's expected to be lower for samples the model has seen during training, a phenomenon we leverage. We break down the text into sentences, each containing 256 tokens, and calculate the model's loss for each. To ensure we're measuring what we intend to, we adjust these loss values using a method called zlib entropy, which helps us differentiate between the text's inherent complexity and the model's overconfidence. For a more formal test, we employ the Kolmogorov-Smirnov (KS) test to challenge the assumption that the perplexity distribution of the model on a specific dataset is the same as its perplexity on newly generated texts. If the model wasn't fine-tuned on the dataset in question, this assumption should hold true. The KS test compares the cumulative distributions of loss values between two datasets and calculates a distance between them. If this distance exceeds a certain threshold, we reject our initial assumption and conclude the dataset has influenced the model, indicating radioactivity. This approach is inspired by similar methods used in image classification but differs from others that rely on aggregated scores from one end of the distribution. In settings where the model's inner workings are hidden or it's not being actively supervised, detecting radioactivity becomes more challenging. For instance, if someone suspects their model's outputs have been used without direct evidence of which specific samples, traditional methods fall short. Similarly, in closed model scenarios where only the model's outputs are accessible, trying to extract full sentences to prove training data misuse is impractical due to the vastness of potential training data. When watermarking is involved, we introduce a detection test applicable across all scenarios. This involves embedding a unique watermark into the model's outputs using a specific method and a secret key. The presence of this watermark can then be tested, challenging the assumption that a text wasn't generated with the specific watermarking technique and key. This is a more straightforward approach, as the absence of the watermark in a large corpus suggests the model hasn't been exposed to watermarked outputs. For detecting watermarks directly in a model's outputs, we propose two strategies based on the level of access to the model. In a closed model scenario, we generate new texts with the model and check for watermarks. In a supervised setting, we specifically use watermarked texts from a known dataset, while in an unsupervised setting, we use new texts likely influenced by the same training data. In an open model scenario, rather than generating new texts, we pass existing sentences through the model and score the likelihood of the next token being part of a watermarked sequence. This method allows us to assess the presence of watermarks directly, offering a clear indication of whether the model has been influenced by specific training data. Section Summary. In this section, we explore methods to detect radioactivity in text, both with and without watermarking, using a language model. We assess radioactivity by observing the loss or perplexity of the model on sentences, and conduct a Kolmogorov-Smirnov test to compare distributions and detect radioactivity. When text is watermarked, we introduce detection tests based on the scoring function and secret key, showing that watermark detection can be performed on texts generated by the model. Section. Filter on scored 2 number 2 grams. In this section, we discuss how to enhance the detection of watermarks in text by introducing a specific filter, which we refer to as a set of 2 grams that are likely to have been part of the training data. We only score tokens if they are preceded by a 2 gram that is included in this set, which we believe could have learned the watermark. This method allows us to concentrate our scoring efforts on 2 grams where the watermark is more likely to have been embedded. In situations where we fully understand the training data, this set is composed of all the 2 grams used during training. However, in unsupervised settings, we still aim to focus on sets of tokens that are likely contaminated, such as 2 grams that appear frequently in watermark texts produced by a specific model. It's important to note that we use this filter exclusively in closed model settings. The way we choose the distribution to define this set and generate tokens from it is crucial, and we delve into this topic further in another section. We've observed that detection tests can be empirically inaccurate due to biases in the distribution of tokens, which challenge the assumption of independence. This issue becomes even more pronounced in our case, as the watermark needs to be detected across a significantly larger number of tokens compared to traditional watermarking methods. To address this, we score a token only if its preceding 2 gram hasn't been seen before during detection. This approach ensures more reliable results, even when analyzing a large number of tokens. We provide additional details on the scoring process, methods to improve deduplication, and the accuracy of our tests in an appendix. Our experiments begin with a realistic scenario where a pre-trained large language model, LLM, is fine-tuned on instruction-answer pairs generated by another model. We investigate the radioactivity of watermarked synthetic instructions and compare it to that of non-watermarked instructions whenever possible. For generating instruction data, we follow a specific protocol where we prompt the model with an instruction followed by 3 examples of instruction-answer pairs and then ask it to generate additional pairs. The sampling from the LLM is done either with or without watermarking, using various parameters for logit bias, proportion of green list tokens, and others, employing nucleus sampling techniques. After generating the data, we process it to remove incomplete answers and nearly identical instructions, resulting in a dataset of 100,000 instruction-answer pairs for both cases. We also create mixed datasets with a small percentage of watermarked data, adjusting the total number of instructions to around 14 million tokens but varying the proportion of watermarked ones. For fine-tuning, we train on these synthetic datasets, using the Atom optimizer for 3,000 steps, with a batch size of 8, a learning rate, and a context size of 2048 tokens, which equates to 3 training epochs. We follow a specific learning rate schedule and choose to fine-tune a model trained on different datasets than the one used for generating the instructions to avoid biases. In terms of quality inspection of the instruction tuning, we aim for 2 main goals: generating high-quality instructions and ensuring that the watermark can be detected even in small text segments. We select hyperparameters that allow for a sufficiently wide watermark window to eliminate biases, yet narrow enough for the watermark to be robust to edits. This results in high-quality text while ensuring that the watermark is detectable with a certain level of confidence on approximately 100 tokens. We examine the outputs of the fine-tuned network both qualitatively and quantitatively, comparing scores on various benchmarks. Our findings indicate that instruction tuning does not significantly affect most benchmarks while improving performance on others, and confirms that watermarking instructions does not significantly influence the fine-tuning process. Section Summary. In this section, we introduce a filter on scored 2 grams to enhance detection by focusing on likely contaminated sets of tokens. The filter is based on the preceding 2 gram window and is crucial in closed model settings. We address biases in token distribution that affect detection accuracy and propose a method to score tokens based on unseen contexts, ensuring reliable values even with a large number of tokens analyzed. Section: A baseline with membership inference attacks. In this section, we explore the concept of a baseline with membership inference attacks in the absence of watermarks. We follow the procedure outlined in a previous section for a scenario where membership inference attack, MIA, is possible. Here's how it works. Alice has access to a model and knows all the data generated for Bob in a supervised setting. Bob has fine-tuned this model using a subset of the data, determined by the level of supervision. Experimentally, we distinguish between the model's performance on 2 sets of data using the Kolmogorov-Smirnov test. The first set contains 5,000 instruction answer pairs not used in the model's fine-tuning, while the second set includes 5,000 pairs, some of which were used for fine-tuning. The second set simulates a scenario where Bob generates a lot of data but only fine-tunes the model on a small portion of it. We found that detecting differences becomes harder as the level of supervision decreases because the data contains more texts that Bob did not fine-tune on, making the two perplexity distributions more similar. We also present results from a radioactivity test, showing that when a certain condition is met, the test strongly rejects the null hypothesis, indicating that radioactive contamination is detected with a low probability of false positives. However, as the level of supervision decreases, the test's effectiveness diminishes, becoming random in cases where Alice does not know which data Bob used for fine-tuning. Moving on to scenarios involving watermarking in an open model setting, we study cases where the fine-tuning data, or a portion of it, are watermarked. We discuss how radioactivity detection works in this setting, focusing on the proportion of the model's fine-tuning set that contains watermarked data. We use a watermark detection method on a dataset of watermarked instructions to score big RAMs, representing a significant number of forward passes on texts. In both supervised and unsupervised settings, we repeat the detection multiple times on different text chunks and present the results. Interestingly, in the supervised setting, radioactivity is detected with high confidence even if only a small portion of Bob's fine-tuning data comes from watermarked sources. This is because we only score big RAMs that could be contaminated and are within the exact context seen during fine-tuning. Conversely, in the unsupervised setting, our open model radioactivity detection test still yields significant results when a small portion of the instructions used for fine-tuning originate from Alice's model. This detection is performed on a corpus of texts that does not include samples used by Bob but contains big RAMs likely overlapping with those Bob trained on. Lastly, we examine the closed model setting, where Bob's model is only accessible via an API. In this setup, we prompt a fine-tuned model with new instructions and run detection on its outputs. We create a filter to score tokens based on whether their preceding big RAMs are part of a specific set. Our findings show that filtering significantly improves the confidence of the detection test, especially in worst-case scenarios. In summary, our exploration into membership inference attacks and radioactivity detection, both with and without watermarking, reveals the nuances of detecting unauthorized model fine-tuning under various levels of supervision and settings. Section Summary. In this section, we explore baseline scenarios with membership inference attacks. We investigate the impact of fine-tuning data being watermarked on radioactivity detection in both open model and closed model settings. The detection test's confidence increases with the number of tokens scored, and filtering the data consistently enhances the detection performance, especially in challenging scenarios. Section: Summary and Discussion. In this section, we discuss how membership inference is notably effective in scenarios where one party, let's call her Alice, knows exactly which data were used to train another party's, Bob's, model and has unrestricted access to it. Under these conditions, Alice can confidently demonstrate that Bob has used her data for training, a concept we refer to as radioactivity. However, it's important to note that such unrestricted access significantly narrows the practical application of membership inference attacks, MIA. Despite our method for detecting MIA not being the absolute best, to our knowledge, no technique can bypass this inherent limitation. On the other hand, we explore a method based on watermarking that can identify traces of radioactivity in a model across various conditions. For instance, even if Alice doesn't oversee Bob's training data, a more likely scenario, she can still detect radioactivity if she has access to the model through an API and a significant portion of the data is watermarked. This method proves even more potent when the model is fully accessible, allowing for the detection of radioactivity with greater precision if a substantial part of the text is watermarked. We delve into the specifics of our testing procedures, the accuracy of our tests, and provide visual representations through box plots for our experiments. Additionally, we discuss how the size of the training dataset impacts our findings. Our investigation into what influences radioactivity focuses on three main factors: fine-tuning, the watermarking algorithm, and the distribution of data. Initially, we examine how fine-tuning affects radioactivity detection, considering variables such as the learning rate, the fine-tuning algorithm, the number of training cycles, epochs, and the size of the model. By fine-tuning the model with a dataset of watermarked instructions and varying one parameter at a time, we observe that the more closely the model aligns with the fine-tuning data, the easier it is to detect its radioactivity. For example, increasing the learning rate significantly enhances the detectability of radioactivity. Furthermore, we introduce variety in our data by using prompts from Wikipedia articles in English and generating responses with and without watermarking. This approach allows us to explore the effects of watermark window size and data distribution on radioactivity detection. We find that smaller watermark window sizes lead to higher detection confidence, likely due to increased repetition and memorization of smaller sequences in the model. Conversely, as the window size grows, the detection confidence diminishes. When considering data distribution, we simulate a scenario where Alice lacks prior knowledge about the data's characteristics, such as its language, used by Bob for training. By running tests on texts generated in various languages, we demonstrate that the effectiveness of the radioactivity test varies with the language's similarity to the training data. However, by combining the significance levels of each test, Alice can still assess the presence of radioactivity across different data distributions. In summary, our exploration into model radioactivity, through the lenses of fine-tuning, watermarking, and data distribution, reveals nuanced insights into the detectability of data usage in machine learning models. This not only advances our understanding of model behavior but also enhances our ability to safeguard data privacy in machine learning applications.